Swayam Prabha. Digital India. Educated India.
So now what we will do is, we will not bother ourselves with lifeless quantities like xz, yz, z square, right. We are going to talk about things that are more interesting to chemists. The question is how to use projection operators to get, that is over enthusiasm, to get SALCs. How can one use projection operators to get SALCs? Let us see. Let us take a simple example. Let us say C2H4. What is the structure of C2H4? I can draw it like this. Ethylene. What is the point group? D2H. And this Mayak, in case you have not noticed, is our exercise in symmetry point group. The only problem is that we are taking really very easy examples. So what I can say is, I can call this s orbital on hydrogen atom sigma 1. I call the s orbital of this hydrogen atom sigma 2, this is sigma 3, this is sigma 4. Okay. So first thing is already known to us, but before that let me define the axis, otherwise it can be pretty confusing. What is the principal axis of symmetry? How many C2 axes are here? 3, right? But this is the unique axis. This is the principal axis of symmetry. This one. In this case we call this the z axis, okay. C2Z. So this is x, this is y, okay. It does not matter because we are going to use x, y, z all the time, okay. Now, how many of us do not have character tables? Henceforth, kindly bring character tables so that we do not have to project. Huh? So, what do we want to do? We want to use these sigma 1, sigma 2, sigma 3, sigma 4, and we want to generate a reducible representative. For that we do not need character tables. We will just write down the symmetry operations. What will you have? You have E, of course, then you have C2Z, C2Y, C2X. Next, is there a center of inversion? I. What else would be there? Sigma XY, sigma ZX, sigma YZ. All are different classes. So now if I use sigma 1, sigma 2, sigma 3, sigma 4 as the basis, what is the representation that I generate? What is the character of E? My basis is sigma 1, sigma 2, sigma 3, sigma 4. Four or 6? Not 6? Sure? It is 4, sigma 1, sigma 2, sigma 3, sigma 4. So there are 4 4-dimensional basis. So, E is 4. What about C2? What is the character of C2Z? C2Z, what is the character? 0, right? Because we are considering separate s orbitals for now. So, 0. What about C2Y? C2X? I? Now this is getting boring. Everything is 0. So, to make more things a little more lively, sigma xy. Sigma xy, don't forget what is x, what is y. xy is the molecular plane, 4. Sigma zx, sigma yz, 0. This is like the score of the Indian team in that disastrous match against England. Right? 1, 2, 3, 4, 5, 6, 7, 8. The other 3 people scored maybe 10, 11, and that's how we got that score. Okay. If you break this down, I'll call it gamma sigma maybe. I'll spare you the trouble of working it out, and I'll give you the answer. It is AG B1G, AG plus B1G plus B2U plus B3U. Okay, you have to just believe me on that, or you have to work it out. Now let us see the character table. Yeah, I understand the confusion. We have only talked about 1 and 2 so far. But then if you have more than 2 B's, what will you do? You have to give preference to something else also. What is this? D2H. Too good is no good. You make it too large, you lose out on resolution. Now, this is beautiful. Huh? Okay. So, see what we have here. 1, 2, 3, 4, 5, 6, 7, 8. 8 classes means 8 irreducible representations. What are the dimensionalities? 1 each. You can work that out, I believe. So, now you have AG. Okay, only one AG kind of representation is there, so you don't have to call it A1G. AG is enough. See. Now, next the problem is you have, and once again, AU kind of representation also is only one. Okay, what is it that makes it B? What is it that makes it B? Character of, no, first B, forget about everything else. Yeah. So, Z is C2Z is negative, -1, -1, -1, -1. That is what make them B. But there are 4. So, we can try to classify further using G, right. So, the problem that you get is that you get 2 G's and 2 U's. Actually 3 G's and 3 U's. Now, let us focus on B1G, B2G, B3G. Why have we called it B1G? C2Y is plus. Here C2Y is minus. I wish I had a ruler. I am getting parallax. This is B3G, right? Just let me draw the line. B1G this is -1, this is -1, this is -1. So, now you go by this XZ, then you call it according to that. I do not exactly know which one is used to make it 2 and 3, but then let us go by the character table. This is what you get. Now, what do we need to do now? We need to use the projection operators. Let us use the projection operator of AG. AG is one of these or not? Yeah, AG. Projection operator of AG on sigma. Can you do that? Projection operator of AG operating on sigma. What will happen? So what I want is, I want projection operator of AG operating on sigma. What will I get? Characters are all one, that is a good thing. It's AG, okay, and the functions also remain unchanged under which operation? E. So to start, for E, what will be the term? Sigma, right? Because R, what is Pj hat? I hope you have not forgotten that. It is sum over R chi R j multiplied by R hat. So basically what you have to do is, you have to make R hat operate on that function and then multiply it by the appropriate character, right. So for the first one, E operates on sigma to give sigma, multiplied by 1 is 1 sigma. What happens when C2 operates on sigma? When C2 operates on sigma, C2Z, what do you get? What am I doing? Sorry, I completely forgot the one. Sigma 1, sigma 2, sigma 3, sigma 4. These are the 4 functions, right? I take the first one, sigma 1. You can take any one, doesn't matter. You can take sigma 2, sigma 3, sigma 4, anything. But I want to take first things first. So I have taken sigma 1. I am operating the incomplete projection operator of AG on sigma 1, and I am trying to see what I get. So first term is, R is E here, E operating on sigma 1 is sigma 1, multiplied by 1 is sigma 1. What happens when C2Z operates on sigma 1? What do you get? Sigma 3 multiplied by 1, that is sigma 3. What about C2Y? C2Y, Y is here. Sigma 4 multiplied by 1, sigma 4. So you see what's happening? We are generating a linear combination. Plus, what happens when C2X operates on it? Sigma 2. Then what happens when I operates on it? I, sigma 3. What happens when sigma XY operates on it? What happens when sigma ZX operates on it? What happens when sigma YZ operates on it? What do I get? I get a 2, which is outside, but don't forget we have not even considered Li by j, right? So essentially, if I forget about the common coefficient, I get sigma 1 plus sigma 2 plus sigma 3 plus sigma 4. So what is this? This is the AG SALC that I can generate using sigma 1, sigma 2, sigma 3, sigma 4, right? Understood? Now, if I want to normalize this, what would be the normalization constant? So this is your normalized SALC, which has AG symmetry. So what I am saying is, the example that we took earlier, xz plus yz plus z square, what we did is we made this the projection operator operate on it, and we projected out the components that had the right symmetry. Now what I am saying is, the reverse is also true. You take one of the components and make the projection operator operate on it. Of course, we have cheated a little bit because we have not taken the complex conjugate. Complex conjugate here is the same. So what we are doing is, we are making the projection operator. So when you make the projection operator operate on a linear combination, then you get the components. When you use the projection operator on the components, you get the linear combination. Okay, but life may not be all that simple, as we will get to see eventually. Okay, what about the next one? Character table will be required. I hope you are not forgotten that this is x, this is y, z is pointing towards us, and what I want next is projection operator, incomplete projection operator of B1G operating on sigma 1. What I will do is I will just read the characters to you. B1G, right? The characters are 1, 1, minus 1, 1, 1, minus 1. Sorry, I repeated what I said. So, 1, 1, minus 1, those are the first three. Then fourth one is minus 1, fifth is plus 1, sixth is plus 1, last two are minus 1, minus 1. I will read again. 1, 1, minus 1, minus 1, 1, 1, minus 1, minus 1. That would have been the easiest thing to say in the first place. 1, 1, minus 1, minus 1, 1, 1, minus 1, minus 1, 1, 1, minus 1, minus 1. It's like, sounds like a mantra. So, knowing the characters to be 1, 1, minus 1, minus 1, 1, 1, minus 1, minus 1, can you tell me what you get by making the partial projection or the incomplete projection operator corresponding to B1G operate on sigma 1? Sigma 1, then plus sigma 3, very good. Normalization constant will be the same. Now, what is the next one? Next one is B2U. So, projection operator of B2U operating on sigma 1. Projection operator of B2U. So, I will tell you what is this? B2U, right? B2U is 1 minus 1, 1 minus 1, minus 1, 1, minus 1, 1. I repeat, 1 minus 1, 1 minus 1, minus 1, 1, minus 1, 1. Make it operate on sigma 1 and tell me what you get. I will write the half outside for you. Sigma 1 minus sigma 2 minus sigma 3. And what happens when projection operator of B3U operates on it? Now you are guessing. Huh? I haven't even told you the characters. B3U is 1 minus 1 minus 1, 1 minus 1, 1, 1 minus 1. 1 minus 1, minus 1, 1, minus 1, 1, 1 minus 1. I might as well write the answer sigma 1 plus sigma 2 minus sigma 3 minus sigma 4. Okay. Now, can you just tell me whether I say this SALC is normal to this SALC or not?
These are ungenerated or battle, right? B2U. So, character for sigma 1, sigma 3 or something, which is in C2, something will be negative, right? Other than A1 and G.
So, these are negative, right? Sigma 1 minus sigma 2. Are you talking about character or coefficient? Characters, of course, negative character, negative minus 1 plus 1 are there. Which one? You are talking about character of I. Huh? Character of I of B3U is minus 1 and character of I of B2U is also minus 1 unless I read it incorrectly. Ungenerated, of course, is minus 1. So, this is how you generate SALCs.